Hello everyone. In this problem session, I will solve some problems about limits of functions at certain points. I will not use L'Hopital's rule, even if I have certain indeterminate forms. I may classify the limit problems into two main groups. In the first group, we have some simple problems. We just plug the number in the expression and get the answer right away. But in the second group, we have some indeterminate forms. We have two ways to solve indeterminate forms for limits. The first way, we can use L'Hopital's rule. Or we may simplify the expression or substitute the expression and take the limit of new form of the expression. Now let's solve an example for the first kind of the problems. When x tends to 1, for this expression, just plug the number 1 in the expression. We have 1 minus 1, which is 0, over 1 square, which is 1, plus 1 is 2. So we directly get the answer. What about the second problem? If you plug the number 1 in the expression, you have 2 over 0, which is an indeterminate form. And in the second expression, if you plug the number 1 in the expression, you have again an indeterminate form. So we must simplify this expression. But as you see, in the denominator of the first fraction, we have difference of squares. It means that we have x minus 1 times x plus 1 in the denominator of the first fraction. So if you multiply the second expression by x plus 1, we have 2 minus x plus 1 over x squared minus 1. Let's simplify this expression. 2 minus 1, we have 1, minus x over x squared minus 1, when x tends to 1. And finally, I re-express the denominator of the fraction as the multiplication of x minus 1 and x plus 1. If you cancel this term, you have minus 1 over x plus 1. Plug the number 1 in the expression. You have minus 1 over 1 plus 1, which is 2. As you see, it's not so difficult to solve the problem. Now let's take the limit of certain trigonometric functions. To solve this kind of problems, do not forget that when x tends to 0, we have 1 for sine x over x. It's very important to remember this fact. When x tends to 0, you have sine 0 over sine 0, which is 0 over 0. We have an indeterminate form, but we can do something. When x tends to 0, instead of sine x, I rewrite the expression as sine 3x over 3x times 5x over sine 5x. So, since I divide the expression by 3x and multiply by 5x, I multiply all this expression by 3x over 5x. So nothing is changed. And we know that sine 3x over 3x is 1 when x tends to 0. 5x over sine 5x is also 1 by this fact. when x tends to 0. So we have limit of 3x over 5x. If you cancel this x, we have 3 over 5 as the answer. In the second problem, we have a general form of the first problem actually. So we can write sine x over ax, sine ax over ax instead of ax. And I write bx over sine bx instead of sine bx. So I divide the expression by ax and multiply by bx. So I should multiply the whole term by ax over bx. And I know that when x tends to 0, this term is 1, second term is also 1. And if you cancel this, you have a over b as the answer for general cases. We use exactly the same idea in this problem. When x tends to 0, instead of tangent x, I write sine x over cosine x times 1 over x. I want to rewrite the expression as sine x over x times 1 over cosine x. We know that when x tends to 0, sine x over x is 1. And when x tends to 0, again, 1 over cosine 0 is 1. So the answer is 1. What about the second problem? Limit when x tends to 0, sine ax over bx. I need ax in the denominator of the fraction, and since I divide by ax, I should multiply by x, and I have bx from the problem. When x tends to 0, I know that this term is 1, and if you cancel this x, you finally have a over b. Now let's look at a more complicated problem. Do not forget again that when you have a square root or root expression in your problem, just multiply the expression by the conjugate of root expression. So let's multiply the expression by its conjugate. I multiplied and divide the expression, the given problem, by the conjugate of this root expression. In the next step, I want to simplify the expression by the formula of differences of squares, which is a square minus b square is a plus b times a minus b. We have square of this expression, which is x plus h, minus square of second expression, which is x, over denominator. I have h in denominator of the fraction. Let's cancel this h, and you also can cancel this. After canceling x, we cancel h, and we finally have limit when h tends to 0, 1 over square root of x plus h plus x. Plug the number 0 in the expression. For h, you have 1 over square root of x plus 0, which is square root of x, plus square root of x, 2 square root of x. I will use the same idea for the second problem. When x tends to 0, square root of 1 plus x minus square root of 1 minus x over x. I will multiply and divide the expression by the conjugate of the numerator. Again, by the formula of differences of sequences, we have, if we simplify this expression, finally we get limit when h tends to 0, 2x over square root of 1 plus x plus square root of 1 minus x. This is x. When x tends to 0, plug the number 0 in the expression. Then we have 0 as the answer, since in numerator we have 0 over 1 plus 0, which is 1, and 1 minus 0, which is 1. 1 plus 1 is true. 0 over a number is 0. So it's done. Let's look at another example. It's a very simple example. Just plug the number 0 in the expression. Then we have 1 plus cosine 0, which is 1. 1 plus 1 over 0. The answer is infinity. If you plug the number 0 in the expression, you have 1 minus cosine 0, which is 0 in numerator. 1 minus cosine 0 is 0, and 0 is 0. So you have an indeterminate form. So we do not get the answer directly. And I don't want to use L'Hopital's rule. Let's simplify the expression. To solve this problem, I need to remember some trigonometric identities. I write 1 minus 2 sine square a over 2x instead of cosine ax in the expression. Then, if we simplify the expression, we have, I also multiply and divide this form by a square over 4. I divide by a square over 4, and then I multiply by a square over 4. And we know that when x tends to 0, sine x over ax, sine ax over 2 over ax over 2 is 1. So this expression is 1. So we have 2 times limit when x tends to 0, a square over 4. It does not depend on x. So the answer is 2 times a square over 4, which is a square over 2. This example is a little bit different. When x tends to pi over 2, sine cosine x over cosine x. In this problem, I will change the variable. Instead of cosine x, I write t, for instance, another variable. So, when x tends to pi over 2, cosine pi over 2 is 0, so t tends to 0. When x tends to pi over 2, t tends to 0. So we should rewrite the problem. Limit when x tends to p over 2, t tends to 0. Instead of cosine x, we have t. So the problem becomes sine t over t. As you see, we know this expression. The answer is 1. Let's look at another example. Limit when x tends to 1, cube root x minus 1 over square root of x minus 1. I want to change the variable again. Instead of cube root x, instead of this, I want to write t. I want to change the variable. So x in this case is t to the power 6. What about when x tends to 1, t tends to, when x tends to 1, t also tends to 1. So we do not have a problem with this. Let's rewrite the problem. Limit when t tends to 1, t square instead of this expression. We have t square minus 1 over t cube minus 1. Limit when t tends to 1. I rewrite the expression. Instead of t square minus 1, I write t minus 1 times t plus 1. Instead of t cube minus 1, I write t minus 1 times t square plus t plus 1. Plus 1. So we cancel this part and we have plug the number 1 in the expression. We have 2 over 1 plus 1 plus 1, which is 3. So the answer is 2 over 3. Actually, we really must understand the idea of limit. Otherwise, we cannot solve all problems. For instance, for simple problems, we directly plug the number in the expression, but it's not the idea of limit. Let's look at this example. We have absolute value. We have two expressions of absolute values in the problem. So we must be careful about this. In order to have a limit value for an expression, we must have limit from right and left. Examine this problem when x is the interval minus 1 to 1, minus 1 over 2 and 1 over 2, since the point 0 is in this interval. So when you approach point 0 both from right and left, and this implies that absolute value of 2x minus 1 is always minus 2x plus 1. Minus 2x plus 1. Let's go back to the limit. Limit when x tends to 0. Instead of absolute 2x minus 1, we have minus 2x plus 1. And since when x tends to 0, inside of second absolute value function is positive. Minus 2x, we have minus 2x minus 1 over x. Let's substitute this limit. This problem is also a similar problem. We have limit when x tends to a, sin x minus sin a over x minus a. It's again an indeterminate form, since when x tends to a, we have sin a minus sin a in numerator, and we have a minus a in denominator of the expression. So we have 0 over 0 indeterminate form. We should simplify or write an equivalent form of this expression. Let's start to solve the problem. This limit expression is equal to limit when x tends to a. Instead of sin x minus sin a, I write 2 times cosine x plus a over 2 times sine x minus a over 2. We have x minus a in the denominator of the expression. You may wonder, how do we get this trigonometric identity? Let me explain. We know that sine of x plus y is equal to sine x times cosine y. plus cosine x times sine y. For x minus y, sine of x minus y is equal to sine x times cosine y minus cosine x times sine y. By these two equations, we have sine x plus y minus sine of x minus y is equal to 2 times, we cancel these two terms, 2 times cosine x times sine y. If we substitute this expression, we have this equality. Now let alpha plus beta is equal to x and alpha minus beta is equal to y. Let x plus y is equal to alpha and x minus y is equal to beta. If we solve this system, we have x is equal to alpha plus beta over 2 and y is alpha minus beta over 2. If we plug these two values in this equality, we have this expression. Then we have limit when x tends to a, sine x minus a over 2 over x minus a over 2 times cosine, this part, cosine x plus a over 2. Again, we know that this term is 1 when x tends to a. So the answer is 1 times cosine a. In this problem, we have 0 over 0 indeterminate form when x tends to pi over 4. So let's simplify the expression. I write sine x over cosine x instead of tangent x in the problem. After two steps, I have cosine x times sine x minus cosine x over cosine x minus sine. This expression is minus 1 when x tends to cosine x. When x tends to pi over 4, cosine x is 1 over square root 2. So the answer is minus square root 2 over 2. This problem is also nice. I will use trigonometric identities instead of sine x plus h. Sine x plus h. We know that sine x plus h is equal to sine x times cosine h plus cosine x times sine h. I will plug this expression in the given problem. Let's simplify this expression. We have, I take the parentheses of sine x, so we have cosine h as the coefficient of sine x and minus 1. Take the parentheses of sine x, we have cosine h minus 1 over h plus limit when h tends to 0, we have cosine x times sine h. Over h. We do not have a problem with second term since when h tends to 0, sine h over h is 1 and 1 times cosine x is cosine x. But what about the first term? We have a problem. When h tends to 0, cosine 0 is 1, 1 minus 1 is 0. We have 0 over 0 indeterminate form. Let's use a trigonometric identity to redefine cosine h. Instead of cosine h, we have 1 minus 2 times sine square h over 2 minus 1. So let's substitute the final expression we have. I had one redundant one and I deleted this. So the answer when h tends to 0, 1 minus 2 sine 0 is 0. So we have 1 minus 1, which is 0 over h. So the answer is 0 times sine x plus, when h tends to 0, sine h over h is 1 times cosine x. So the final answer is cosine x. In this kind of problems, it's really important to remember the formula of some trigonometric functions. I think we need to remember at least 3 fundamental trigonometric identities. One of them is cosine x plus or minus y. And the second one, x plus minus, sine x minus plus y. And the third one, x squared minus sine square is equal to 1. If you remember these 3 identities, you may produce any trigonometric identities. This is end of this problem session course. I will continue to solve some problems for limits.